Hi, and welcome back to another exciting session of material for Engineering 102. Right now what I'm wanting to do is go over the solar oven and try to explain with respect to dimensions and geometry and the equations how we can come up with the equations that will help us describe the inside oven temperature, or T sub IO, in this oven relative to the different parameters in the system. We have, for our solar oven, a box within a box, and I've tried to draw that here. The outer box is in green. The inner box is what I'm calling the cooking chamber, or the oven baking area, and that actually has dimensions in the top surface and bottom surface. I'm going to assume that this is a cube or a rectangular structure. It doesn't have to be the same depth as it is long and wide, but the length is going to be from the front, the width is across the front, and the depth will be down into the outer box, and that will then describe our particular inner chamber or oven area. The area of the window is really this top surface, and if I shade that, that area of the window is, I hope, clearly the length times the width. If it's going to be important when we talk about this particular oven to have a pretty good perspective on the different views or ways of looking at that box within a box, and we'll talk about maybe the top view, looking down at the top of the oven. We may have a side view if we looked at it, let's say, from the left side, and we might have a front view, and hopefully those views will allow us to determine some of these areas that we'll be dealing with when we start worrying about heat transfer coefficients and how we're losing power out of this oven when we do our power balance, which is possible because we have, on average or over the course of time, we have an energy balance and we reach a temperature equilibrium inside the oven cavity. In order to achieve that equilibrium, we need to set up our oven so that it's optimally oriented towards the sun. This particular vector that I've shown here is the angle with which the sun is hitting the earth at the appropriate time of day and in the appropriate location where we're at. That we're calling theta sub s. What we want is to have our box front, or the window, perpendicular to the sun, and in order to achieve that, since we're assuming we have a rectangular box, this is a right angle. Here's the angle of our sun, theta sub s. Beta is the box angle, and I think it's pretty clear that those all have to sum up to this straight line, or an angle of 180 degrees. Meaning we now have 180 degrees is equal to 90 degrees, that's this rectangular box corner, plus our sun angle, theta sub s, plus the angle of our box, beta. If we solve for theta sub s plus beta to optimally heat this oven, we actually need that to be 90 degrees, and we'll try to keep our box tilted at the appropriate beta such that the sum, theta sub s plus beta, during the testing of our ovens is always maintained at 90 degrees. We're just going to assume that. The other thing that we are going to assume is that the power hitting the earth where we are at, we're going to assume that that's 1,000 watts per square meter. And obviously, with respect to that, it's not going to, with respect to our particular oven, our oven obviously is not going to be receiving 1,000 watts in the area that it has available to it, since our window is not nearly that large, since one of our constraints is to have an oven chamber or inner box of volume 1,000 cubic centimeters. Here are those views again. If we just looked at the top-down view, on the left is where I'm saying is the length, and on the right it's the same length. Then the front, and I'm going to sort of call this the bottom side here, and the top side there, that has a width of W, and I believe we're going to go ahead and assume that length and width are the same, and we then have a square window and a square bottom to our particular inner box. If we looked at this box within a box from the left-hand view or on a side view, then we're looking at a length from right to left, and the depth is one of the design parameters also that we get to select, although the depth, we're told, needs to be at least 5 centimeters in depth. So we're constrained, we can't have it too shallow in terms of that dimension, the depth dimension. If we looked at the front, if we got down on the floor and stared into the front of this box within a box, if it was lying flat on the ground, it would look like this front view with the depth now down towards the ground. And all of this particular area, if we looked inside the box, could be our insulating material, which might be wadded up newspaper. The cardboard aspect is actually going to be, here's some cardboard width and here's some cardboard width. That would be on, let's say, the left side. We would have a cardboard width there and a cardboard width there, and the newspaper insulation, that would be on the bottom. On the right side, we would have cardboard in purple, green newspaper, and cardboard. And I think we're told that the cardboard is 3 millimeters, and you'll want to make sure that your dimensions, you probably want to convert all of those to meters when you start using those equations. If we were looking at the side, if we walked around the box and got on the left side, then we also have a similar configuration in terms of cardboard, newspaper, and cardboard. And again, these purple might be the 3 millimeters. In your first homework assignment, this particular distance is 75 millimeters. And in the homework, they're also assuming that this cardboard on the bottom of your inner box and on the bottom of your outer box, in addition to your newspaper, they're assuming that that newspaper on the bottom is likewise 75 millimeters. You may not want it to be that in your oven, but to make the simplest equations when we get there, you'll find that it's probably easier in terms of one formula to have a symmetric insulating volume around your inner box, meaning the distance between your two cardboard inner and outer surfaces on the left, which is right here, on the top, which is right here, on the top side, on the bottom side, and then underneath or in the bottom, all of those, and on the right side, they're assuming that those are all the same. If you need to start calculating areas, which we will when we start talking about how much loss we're having out of the oven, we need to actually compute several areas and then put them all together. And we're really separating this into two types of, or two locations where we might lose power in that oven that we're dealing with. One is out the window through the top, and that window has an area of length times width, L times W. Then we have all of this area that's associated with the 5 remaining surfaces of our inner box. We have the very bottom of our box, which is equal in area to the top window surface. That's L times W. Then we have the left side and the right side of our box, which if we go back to the top view, what I'm saying there is we now have underneath or just below where I am indicating right there, just below that is going to then be the left side. Here's the right side, and then we have the top and bottom sides, where the bottom side, try not to get that confused with what I'm calling the bottom. But those particular left and right will be D times L. Bottom and top sides will be D times W. And obviously if L and W are constrained to be equal, those left, right, bottom, and top sides will all be the same in terms of D times L or D times W. Here's another depiction of that in a three-dimensional setting. It's maybe a little bit difficult to see what I'm trying to do. There's the window. That's the top surface. And that's has a length of L and a width of W. That's the same as the very bottom surface, which is what I'm saying is right there. That area is length times W. And then we have the four sides around the perimeter of that rectangular or parallel pipette box. We have the left side, which is over here. We have the right side over there. Then we have the bottom side, which is, you could think of it as in this picture, the front side. And we have the top or the back side of that surface of a box. Now that we have all of that, and hopefully we have a feel for this box within a box, what we want to show is that we really have an energy balance, which over time, or if we divide out time, we actually have a power balance, meaning the power absorbed or the power in is equal to the power out, or the amount of power that we lose. We will use that relationship to actually determine the internal oven temperature, or T sub IO. Let's now spend just a few minutes talking about the left side and the right side, or the absorbed power and the output, or the power that's lost. And I've been telling students before that if you think of this similarly to how you might think of filling up a bucket with water. If this is now our inlet water flow, we'll make that blue for water, and this black is, think of that as a bucket. And now suppose that I drill a few holes in the bottom of this bucket. If it just turns out that the amount of water flowing in is balanced by the amount of water flowing out of these holes, then, and that will be true once this gets to a particular height, that height will stabilize, and now we'll have a constant height if the liquid flow in equals this liquid flow out. And that really sort of the velocity with which that water flows out, or the rate at which it flows out, will be influenced by the height of this. But in this particular analogy, if we can find this right inlet flow with the outlet flow, we'll be able to stabilize at a fixed height. That's similar to what we're doing with the oven. This inlet flow is actually the amount of power that we're getting or collecting from the sun, or that's our absorbed power. And what we can't keep in that inner box, some power actually is going to flow out of that inner box, going back to the very first picture, and that power escaping from the inner box is what we will then use, or we'll find an equation for that, and the lost power, or the power out, equaling the input power, will allow us to reach a thermal equilibrium, and we can then use that to solve for this height of our liquid in the bucket, or really the temperature inside our oven. Let's now look at those two pieces. We have the power absorbed. And all of that begins with how much power the sun is actually delivering to the Earth's surface, and that usually is just given as this power density of the sun being, or incident solar power density, in watts per square meter. And now if you think of basically a card table tabletop, that's roughly a square meter. If we could put that perpendicular to the sun and we had a really good collecting surface, that would, well, the sun would hit it or be incident at 1,000 watts on that particular surface. We obviously do not have a square meter surface area for our oven window. We have much less than that, but this is where we can start, and then we'll multiply that by the window of our oven in order to determine how much power we will have hitting on the particular window. For example, if this box that we have is now adjusted to where the box angle, beta, this is now the incident sun angle, or theta sub s, and here's our 90 degrees. We're assuming now that theta sub s plus beta is 90 degrees. Now we can capture all of that incident power from the sun on our window surface. And so the power incident on our particular oven is actually going to be the length of the window times the width of the window times I sub 0. And if we weren't able to satisfy this condition, we would need to sacrifice some of that power by the sine of that angle theta sub s plus beta. What we want to do is maintain or keep beta adjusted, if we're doing this over the course of time, such that beta plus theta sub s is 90 degrees. This becomes 1, and now the incident power is what we will call the area of our window, A sub w, which is that product, times I sub 0. That's now what we have incident on our oven. We're not going to be able to transmit all of that through or into the oven cavity or this inner box because we're making it go through this, let's say, mylar window. So we are going to have then a slightly reduced power from the incident power, and it will be reduced by this transmission coefficient tau that is caused by the transmission properties of our window. And in our case, it's probably going to be this mylar sheet. So now we have this incident power getting reduced, and typically for one particular mylar sheet, we have tau. If we doubled that up, we would have tau squared. And the tau that we will use, now I'm going to lose what we've actually decided we will use for tau, but I'm thinking that's in the 0.92 range, if I could find that in the notes somewhere. But I'm going to just say, let's just assume that that's 0.92. That's the amount of power that's transmitted through the window. We now need to collect that or absorb that power, and so the actual power that comes in to our oven cavity we will call the absorbed power, and that will be the transmitted power scaled by this absorption coefficient, where A, let's say, is now 0.9. That's now the input power, or that's the amount of water flowing into our bucket, and that's going to basically determine what we get for an internal oven temperature. And if we could keep all of that heat in, we could get a pretty hot oven, or if we could keep all of that power in the inner box. But that's not going to happen, and what we need to do is figure out how much power we are losing out of the box. Remember our inner box, and now I'm not sure how I really want to draw that, but let me say that let's do a cutaway of our box within a box. And what we're going to have is we will have some power lost out the window. We will have some power lost out the right side, some power lost out the left side, and some power lost out the bottom of our surface. And we will also have it on the front, bottom, and the top surface on the four sides of the perimeter of our inner box. And we may just lump all of that together into the sides and bottom being one heat loss because they look very similar. We're going to have cardboard, and maybe some newspaper. That looks the same here, here, and here as long as the distances between the two cardboard pieces are the same. So we'll maybe initially treat those the same, but I hope you can see how to generalize that to a more accurate picture if you do have this particular distance down below the oven different from this left side, right side, or front and top dimension in terms of the distance between the inner box sides and the outer box sides. Let's not worry so much about that right now, but now what we do have to worry about in terms of this discussion is that we have now temperature out here, which we call the ambient temperature, and we have the temperature inside the oven, or T sub IO. This temperature gradient goes from hot to colder locations or spaces, and what we want to do is try to minimize that heat, or yes, the heat transferred between the hot temperature and the colder temperature, which is our ambient temperature. And we might, for design purposes, just think of that being 21 degrees C for now. What we want to do, though, is figure out what is this output power that we're losing out of the sides and the bottom and the window. We're going to lose some out of the window, and that's going to be related to this heat transfer coefficient, U sub W, times the area of the window times the temperature gradient, T sub IO minus T ambient. That will be the power lost out of the window, and we'll have, if we assume all of the dimensions between the cardboard sides and the inner newspaper, we have the heat transfer coefficient of the sides and the bottom times the area of the sides and the bottom times this T sub IO minus T ambient. Now, what you need to keep track of is that this area includes the 5 remaining sides of your inner box or oven chamber, and that's going to be the bottom surface of your inner box. It's going to be the left and right side, which is, let's say, the length times the depth. You have 2 of those, and now you have the bottom front and the top surface on the sides, and those will be depth times width. You'll have to include all of those as well as the bottom of your inner box. Those are all making up this area of the sides and the bottom. This heat transfer coefficient in the sides and the bottom and in the window are what we now need to worry about. But what we can try to get comfortable with is what this really means. We know that power is in watts. This we're pretty comfortable with. That's temperature, degrees C. This we're pretty comfortable with. That's area. In terms of SI units, that's meters squared. What we now can figure out is that the units on this heat transfer coefficient must be watts per meter squared degrees C, where those are in the denominator, which when we multiply it by the area of either the window or the sides and the bottom and the temperature difference, TIO minus T ambient, we are going to get watts. And what we want to do is minimize the amount of power that we're losing out of the oven. We want to crank this guy up, so this piece we want really to be as big as possible. This piece and that piece will depend on how big we make our inner box, and this is what we can now, well, we may have to live with U sub W because the Mylar, if that's what we use for our window, this now will be a function of the particular design that we use, but on the, let's say, here's our inner box, here's our outer box, and here is our newspaper, wadded up newspaper. This heat transfer coefficient is going to be dependent on the thermal conductivity of the cardboard. It will be dependent on the thermal conductivity of our newspaper, and it will also depend on these distances, where this is maybe Kx sub 1, or maybe this, let's say that's x1, this is x sub 3, and this distance is x sub 2, and let's assume that these have a heat, let's say that these now have a thermal conductivity of K1, K2, and K sub 3. We can't just add those up. In fact, this heat transfer coefficient, U sub, let's say, sides and bottom, and this might just be, let's just say for the left side for now, would be equal to, and it's really, if we just had the one to worry about, it wouldn't be so bad, but we actually have 3 of these, and they don't just sum up. We actually have to worry about their resistance to heat flow, and really that's related to the reciprocal. And this is going to then be this 1 over K1 divided by X1 plus 1 over K sub 2 divided by X2 plus 1 over K sub 3 divided by X3. What we want is the U sub SB for all of them. Right now we're just saying that we'll look at the left side, and if we make all of those dimensions symmetric, then we can just say that, well, we have the same cardboard on the inner oven, we have the same cardboard width on the outer box, and we have the same amount of cardboard in between those separated, we have the same length of newspaper or depth of newspaper on in between those cardboard surfaces. So that now this U sub SB, or the thermal conductivity, or the heat transfer coefficient, I should say, of the sides and the bottom is now 1 over this 1 over K1 over X1, but if we now simplify that, we will have X1 over K1 plus X2 over K2 plus X sub 3 over K sub 3. And you'll need to make sure that the units end up being watts per square meter degree C, and that you're working with consistent units. And where you might get into trouble is using millimeters instead of meters. If x1 is a distance, you want to make sure that that's in meters. And I think some of the ones that we will be using is the thermal conductivity of cardboard. In the handout or in the packet is this 0.064 watts per meter degree C. Use meters for x1, and then your newspaper, wadded up newspaper, is a little bit higher in terms of its thermal conductivity, and that's 0.123 watts per meter degree C. That will now allow you to compute U sub SB, and if you have symmetry on the left and right, very bottom, and in the front surface and top surface, then U sub SB will be the same, and your area, then you can just figure up what that is for the bottom of your inner box, what it is for the left and right side, what it is for the front and back, and that's now your area of sides and bottom. So that's going to be the area of the bottom plus 2 times the area of the sides of your box plus 2 times the area, let's say, of the top surface, where this is just LW, this is L times D, and this is W times D. If we assume L and W are the same, then you get the same value for those. Now that we have those expressions defined, we now know that the output power is going to be the heat transfer coefficient, U sub SB, times the area of the sides and the bottom, times T inside our oven minus T ambient, plus the heat transfer coefficient of the window times the area of the window times this temperature gradient, which is the inner oven temperature minus the ambient temperature. We can now factor the temperature gradient out, and we're left now with our output power formula, P out. And remember, we want to reach thermal equilibrium. Because of that, we are going to want, or we will be able to say, that the power absorbed, or the input power, is now equal to the output power. Setting those two equal to each other, if we remember what those were, over here we had A times tau if we just had 1 Mylar sheet. If we had 2 Mylar sheets, you would have to square that. So you might see this in the notes as tau to the n. I sub 0 times the area of the window. You should be able to calculate that pretty easy. I0 is just 1,000 watts per square meter. Your area of the window is length times width, and A and tau are given to you. The power out is now U sub SB, A sub SB, plus the heat transfer coefficient of the window times the area of the window times T sub IO minus T ambient. What are we trying to do? We're trying to find our ambient temperature, and if we solve that equation for the ambient temperature, we can divide through by this heat transfer coefficient times area sum and add T ambient to both sides, and we now are left with the following equation for determining the inner oven temperature. Based on what you've now computed for the area of the sides and the bottoms. That's the 5 sides other than the window. Here's the window area. This U sub SB was that formula that we had to worry about having cardboard, newspaper, cardboard combined. This is the window heat transfer coefficient, and that is where the problem lies. This heat transfer coefficient is temperature dependent. And because of that, what we are going to do, if we solve this graphically, what we want to do is we're given by measured data in the packet on page 9 of the 37-page packet. Somebody has now collected this data such that the temperature of, or when this Mylar sheet is at a given temperature, they've now measured its heat transfer coefficient. For example, at 66 degrees, they've determined that the heat transfer coefficient in watts per square meter degree C is 10.10. At 93 degrees, they've measured it to be 13.9. At 121 degrees, they've measured it to be 18.66. And you can find this in Table 1 of your report, or of the packet that I call it. Here's 149. That's now upwards of 24.34. And this heat transfer coefficient depends on whether you have 1 Mylar sheet or 2 Mylar sheets. I'm just going to talk right now about 1 Mylar sheet so that we're not completely overwhelmed by the amount of data. But you can now plot that. You can plot that temperature that somebody has determined relative to this heat transfer coefficient, which is watts per meter squared degree C, where we're starting at 10.1, and that gave rise to a T sub IO of 66, and that's going to be a point right there, all the way up to 40.11, and our temperature there was 204. And now we just have these other 4 points between those, and this might give us a curve that looks like that. What we want to do now is compare that to what we obtain if we use this equation that we just derived. We now are going to assume that maybe this is 21 degrees. You can calculate this based on your configuration of cardboard and newspaper. This area are the 5 sides that don't include the window surface. Now you may just pick UW to be 10.1 like we did before, because we don't yet know what this I sub 0 inside the oven is. This window area is known. We know what this is. We're assuming a value for that and A, and we've determined what A sub W is. We now have all of that. What we want to do is, for different values of UW, determine what TI0 is from this particular equation. And in so doing, we can now plot that on this same graph. Let me now do that in blue. And if we do that, now at 10.1 for a value of U sub W, or this heat transfer coefficient through the window, let's say that that ends up giving us a temperature up here. Then we might get another temperature of here, 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 etc. We can connect those dots, and the intersection of those dots is actually the temperature where our oven temperature will settle for that combination of design of our inner box and outer box. And let's say that that's now 80 degrees C. If we look at 2 Mylar sheets, obviously this red curve will change, and our blue curve will likewise change, because now we have different parameter values in this particular formula. We now have changed that tau parameter, and we might now, in the second part of this, where you start doing your design with your Excel spreadsheet, you will want to maybe change your oven dimensions so that some of these area formulas are changed, and maybe you'll change the insulating properties of your box or dimensions so that your heat transfer coefficient U sub SB might change. That's what you want to now adjust in order to try to obtain a higher T sub I0, but we don't know what that's going to be necessarily until we plot it relative to or against this heat transfer coefficient of our window, and finding this intersecting point with the measured data that was given to us in the report and that I've plotted in red. I hope that that helps your understanding of the solar oven design.